Okay. Good evening, everyone. I Gaurav Sahu welcomes you all in 2 weeks faculty development program on smart manufacturing tools and techniques for Industry 4.0 under sponsorship from AICTE Training and Learning Academy. Today's session is on additive manufacturing tools and techniques for Industry 4.0, and for that we are having with us Dr. Abhishek Tiwari. Dr. Tiwari received his B.Tech degree in Metallurgical and Material Engineering from IIT Roorkee in 2008. After a short stint at Bharat Heavy Electricals Limited, Haridwar, as an engineer, he pursued his master's degree in ceramic from ENSCI, France. He completed his PhD from Department of Mechanical and Aerospace, Monash University, Australia. He successfully developed a CVT reactor for a graphene synthesis during his PhD. Currently, he is working as a postdoctoral fellow in the field of additive manufacturing at Department of Mechanical and Aerospace Engineering, IIT Hyderabad, India. He has also worked as a research associate on laser assisted material processing at Department of Metallurgical and Material Engineering, IIT Kharagpur. Dr. Tiwari is a reviewer of many renowned journals and has keen interest in tech startups. We welcome you, sir, and request to deliver your valuable knowledge.
Thank you for introduction, and I would like to thank Professor Jitendra Pandey, Dean at Oriental Institute of Research and Oriental Institute of Science and Technology, Bhopal, and also the management at Oriental Institute of Science and Technology, Bhopal, for inviting me for this faculty development program on smart manufacturing tools and techniques for Industry 4.0. And my topic under this theme is on additive manufacturing tools and techniques for Industry 4.0. So the host has already introduced me, and this is my brief research profile. I work on additive manufacturing and graphene coatings for corrosion resistance, materials engineering, corrosion strength of materials, ceramic engineering, nanotechnology, anisotropic thermal conductivity of polycrystalline oxide materials, and control of porous structure of ice templated ceramics. So I have worked as assistant professor in Department of Mechanical Engineering at Bansal Institute of Research and Technology, Bhopal, for 2 years and 3 months after my PhD. And then I joined IIT Madras. So there I worked on various projects on CR3, C2, and ICR based ceramic coatings for erosion corrosion protection and fracture behavior of zircon alloy 4 processed through swedging. So these projects were like sponsored by CPRI Bangalore and NFC Hyderabad, Nuclear Fuel Complex Hyderabad. And in the same department, then I joined as Institute Postdoc Fellow, and there I worked on designing and developing magnesium alloy test specimens using wire arc additive manufacturing and to evaluate the corrosion behavior of additively manufactured magnesium alloys and to evaluate corrosion behavior of selective laser melted ALSI 10 mg alloys. So basically, I have done the corrosion study on additively manufactured ALSI 10 mg alloys, and then I joined as senior material research engineer in Oxygen Medical Private Limited, Sonipat, Haryana. So there I worked as senior material research engineer for designing and developing various medical bioimplants. And I have used their additive manufacturing for polymer implants and injection molding of peak implants. So after that, I joined IIT Kharagpur as a research associate. So there I worked on development of microstructurally, compositionally, and functionally graded components by laser-assisted material processing. And there I worked on developing a functionally graded 316L and Inconel 718 alloy. So Basically, why we develop these functionally graded materials? It's because we need to have different properties as we move from inside surface to outer surface of the samples. So when we need to change the properties within one single component, then this technique is very useful. So basically, additive manufacturing is extension of laser cladding process. So for example, if we use 316L on the inner side, and the outer surface we want inconel 718, and it's functionally graded. That means inside we are using 100% 316L, and then 75% stainless steel, and 25% inconel 718, and then 50% stainless steel, and then 50% inconel, and then 25% SS, and 75% inconel. And on the outermost layer we develop in 100% inconel 718 layer. So this kind of sample making or component making is only possible through additive manufacturing route. And though additive manufacturing is a very expensive uh, technology, and but the cost is reducing over the period of time, and also the quality of the samples and components have increased very much. Like I have seen in last 5 years, from very bad samples to very good samples. So the technology has got advanced in recent years, and this is one of the key areas where India is investing heavily, and in fact much ahead of other countries. And in fact, DRDO, DMRL, defense defense applications are there. So, in fact, defense ministry in India is also interested in this. So, like in India, like all the IITs are getting sponsored on this technology by defense ministry. So, we are now operating in terms of like 100 crores of funding in additive manufacturing field. And then, after in research associate tenureship in IIT Kharagpur, I joined as postdoctoral fellow in Department of Mechanical and Aerospace Engineering, IIT Hyderabad. So here I am working on large area additive manufacturing. So earlier we used to only operate at sample or component level, but now we want to do it on a large area scale. So I was just seeing in like in Amsterdam they have made a steel bridge out of from additive manufacturing. So you can imagine the entire bridge is made using additive manufacturing. So in this design and development of powder-based direct energy deposition system for direct deposition of rocket components we are using. And also when it comes to Industry 4.0, which is advanced version of in fact smart manufacturing. So in this actually like things are connected. Like let's say in our house, if the tank is filled with water on the roof, and then we have to switch the motor, but we have to go manually. Same way in manufacturing, we don't have the idea is we don't have to do it manually, and if things can be done automatically. And nowadays, artificial intelligence and smart manufacturing, so they are combining, and deep data analytics is there to support. And also, cloud computing is very important in this area, because like when we do online monitoring of the systems, then actually large amount of data is created. Let's say we just do like online monitoring of one sample making, then it is creating like 3 GB data for a small period of time. So this kind of data cannot be handled on computers, because let's say you have 500 GB data like hard disk. So that cannot be handled for higher data processes. So we need cloud computing in this area. Now, because the theme is around Industry 4.0, so first I will introduce what is Industry 4.0. So, Industry 4.0 conceptualizes rapid change to technology and industries and societal patterns and processes in 21st century due to increasing interconnectivity and smart automation. The term has been widely used in scientific literature and in 2015 was popularized by Klaus Schwab of World Economic Forum founder and executive chairman. So Schwab asserts that the changes seen are more than just improvement to the efficiency, but they also say that there is a significant shift in the industrial capitalism. And a part of this phase of industrial change is joining the technologies like artificial intelligence and gene editing and to advanced robotics that blur the lines between physical and digital and biological words. So, in fact, when I was doing my internship in Philips Eindhoven, Netherlands, I got a chance. Yes, can you hear me?
Sir, hello.
Yes.
Sir, are you sliding your PPT?
Yes, yes.
So here not visible.
Oh, it's not visible.
Just seeing first.
Oh, you are seeing only first slide. Okay, I will share again. I will share, in fact, the screen. That will be much better probably. Now, is it visible?
Yes, sir.
Okay. So, just this, I explain my profile first and the area of expertise, and then I am moving to Industry 4.0. So now everyone is on like same page with me. Yes. Hello.
Yeah, it is Industry
Yes, sir.
4.0.
Okay. So, so actually, when I was doing my internship in Philips, I know in Netherlands, I got a chance to visit Philips Turnhout, Belgium. So there I saw that the entire plant was run by robots only. There was in fact no even only one human was in charge of that plant, and everything was automated and selection and rejection of the products were also made by robots, and there was only one person and like thousands of robots working in Philips Turnhout, Belgium. So this is like example of Industry 4.0. Obviously, uh, there is significant threat to the situation that we are going to lose a lot of employment because of this, because everything is going to be automated. And now actually like in Germany they have dedicated Industry 4.0 policy where actually they say that they should have smart factories. So, in fact, like no one will be working, and only the computers and robots will be working, and only one person will be in charge. So, there will be significant loss of jobs, traditional jobs, in fact. So, that is a great problem, but that's why there is need to retrain the mindset of people to learn to rescale the workforce in the field of additive manufacturing and Industry 4.0. So, like the future factories will be something like on-demand production of components. Compared to the traditional factories where first we used to produce the component then selling in the market. So in fact in additive manufacturing we can have custom designed components. For example, if a patient need its jaw to be replaced after an accident, so that can be custom made. And like let's say we take imaging of the left jaw, and then right jaw can be produced using additive manufacturing. And some people may have uh, defective jaws or defective in fact nose parts. In fact, I was seeing one medical institute in Hyderabad. So they have done that surgery, and the component of the bone was made using additive manufacturing. So this is like a very very important development in this field. So throughout this, the fundamental shifts are taking place in how the global production and supply networks operate through ongoing automation of traditional manufacturing and industrial practices using modern smart technology and large-scale machine-to-machine communication and Internet of Things. And this integration results in increasing automation and improving communication and self-monitoring. The use of smart machines that can analyze and diagnose the issues with, without the need for human intervention. In fact, you can see the example of artificial intelligence. Let's say you type something in your WhatsApp and it autocorrects. And similarly, if you Google search something on internet, and then you keep getting ads related to the product that you searched for in Facebook. So that's how and sometimes you type in Google and it auto types the next word without even you have typed. That's something related to artificial intelligence, and that is going to be added in additive manufacturing field also, and in the industry 4.0. So that's called smart manufacturing, and it also represents a social, political, and economic shift from digital age of late 1990s and early 2000s to an era of embedded connectivity and distinguished by omni-use and commonness of technological use throughout society, and that changes the ways humans experience and know the world around them. It posits that we have created and are entering an augmented social reality compared to just the natural senses and industrial ability of humans. So, like this is on the left side, we can see an image of warehouse robots operating goods logistics in an Ocado warehouse, and managed and operated through AI systems created by Ocado technology. And on the right side, we can see augmented tablet information of a painting in Museo de Mataro, linking to the Wikipedia's Catalan article on Jordi Arenas. In fact, you can see that now Google has developed Google Lens. So actually, this is an interesting story. In fact, I was in the same department, Department of Metallurgical and Materials Engineering, IIT Kharagpur, and under the same professor, Professor Indranil Manna,
Sir,
who's hello.
sir, again same problem. Once again, you can check.
You are not seeing any slides?
No.
Hello?
Yes, sir. Not see.
No, no.
Visible, sir.
Is visible?
Yes.
Yeah.
Visible,
So,
but first page.
so I have not changed the slide.
Yes.
Yeah, I have not changed the slide. Yeah,
Okay.
we are on the same page. Yeah.
Okay.
So I was in the same department under the same professor where Sundar Pichai did his BTech project, and in fact, short of additive manufacturing is started where Sundar Pichai was doing laser annealing. There is annealing process, but he did using laser annealing in generally we use annealing in furnace, but he was using annealing using laser. Now we are manufacturing user laser additive manufacturing. So this is sort of extension in the same group. And in fact, like when Sundar Pichai visited his hometown in India, someone asked like which flower is this, and he didn't know. So that Google Lens idea came to his mind that like we should be able to scan it and see what it is. So this is something related to artificial intelligence and Industry 4.0. So this is how the now you can see the next slide. Hello.
Yeah, it is.
Yes, yes, sir.
Yeah.
Number 4.
Yes. So this is how the Industry 4.0 technology revolution is going on, and on the left side we can see illustrated understanding of the Internet of Things in a battlefield setting, and on the right side the customers using Amazon Go. That is an example of just workout shopping where integrated technology creates a seamless consumer journey through including computer vision, deep learning algorithms, and sensor fusion. Now, like we discussed Industry 4.0, but we need to see what was Industry 1.0, Industry 2.0, Industry 3.0, and Industry 4.0. So first, we discuss Industry 1.0. That is the first industrial revolution that was marked by a transition from hand production methods to machines through the use of steam power and water power, and the implementation of new technologies took a long time. So the period which this refers to was between 1762 and 1820 or 1840 in Europe and United States, and its effects had consequences on textile manufacturing, which was first to adopt such changes, as well as iron industry and agriculture and mining, although it also had societal effects with an ever stronger middle class. It also had an effect on British industry at the time. The second revolution, also known as technological revolution, is the period between 1871 and 1914 that resulted from installation of extensive railroad and telegraph networks, which allowed for faster transfer of people and ideas, and electricity. And increasing electrification allowed for factories to develop the modern product line, and it was a period of great economic growth with an increase in productivity, which also caused a surge in unemployment since many factory workers were replaced by machines. And the third industrial revolution, also known as digital revolution, occurred in the late 20th century and after the end of the two world wars, resulting from a slowdown of industrialization and technological advancement compared to the previous periods. The production of Z1 computer, which used binary floating point numbers and Boolean logic, a decade later was the beginning of more advanced digital developments. The next significant development in communication technologies was the supercomputer, with extensive use of computer and communication technologies in the production process. Machinery began to abrogate the need of human power. So, as I said, that with the technological advancement, we are losing jobs now, and jobs are more concentrated towards smart manufacturing now. So that's why, like when we are talking about unemployment for the recent mechanical graduates, this is where the opportunity is for all the graduates, especially in additive manufacturing. There is a huge demand, and the traditional demand is going down. And in additive manufacturing, if someone has experience, then definitely there are jobs. And the fourth industrial revolutions, in a sense, fourth industrial revolution is the trend towards automation, data exchange in manufacturing technologies and processes, which include cyber physical systems, Internet of Things, and industrial Internet of Things, cloud computing, cognitive computing, and artificial intelligence. The machines cannot replace the deep expertise, but it tend to be more efficient than humans in performing repetitive functions. And the combinations of machine learning and computational power allows machines to carry out highly complicated tasks. And the fourth industrial revolution has been defined as technological development in cyber physical systems such as high capacity connectivity, human machine interaction modes such as touch interfaces, virtual reality systems, and improvement in transferring digital instructions to physical world, including robotics, 3D printing, also synonyms to additive manufacturing and Internet of Things, big data and cloud computing, and AI-based systems, and improvement to and uptake of off-grid standalone renewable energy systems such as solar, wind, wave, hydroelectric, and electric batteries, lithium-ion renewable energy storage systems like electric vehicle. And the fourth industrial revolution marks the beginning of imagination age. So this is some like new development, and if you have heard of now like moonlighting, so people are doing 2 to 3 jobs in artificial intelligence and data analytics. So this is why, because there is a huge demand, and companies even can't even think of firing those employees. It's because they are highly in demand, and which is not possible in like traditional jobs. So this is where the opportunities are, and people are getting enormous amount of jobs in this area. Now, the key themes that surrounds around in Industry 4.0. So, Industry 4.0 increases the operational efficiency, and four themes that are presented here are interconnections, that is the ability of machines, devices, and sensors and people to connect and communicate with each other via Internet of Things or Internet people. Then, information transparency, the transparency afforded by Industry 4.0 technology provides operators with comprehensive information to make decisions. Interconnectivity allows operators to collect immense amount of data and information from all points in manufacturing processes, identify key areas that can benefit from improvement to increase functionality and technical assistance. So the technical assistance, the technological facility of systems to assist humans in decision making and problem solving, and the ability to help humans with difficult or unsafe tasks, and decentralized decisions, the ability of cyber physical systems to make decisions on their own and to perform their tasks as autonomously as possible only in case of exceptions, interference, or conflicting goals are tasks delegated to a higher level. So we can see that in India, even a few years back, you could see the manual scavenging and manual cleaning of the gutters in the in the in the lanes flowing the garbage, and why a human need to enter the gutters to clean it? That can be done by machines. So that is something that need to be introduced, and that's where the industry 4.0 can play a role. And nowadays, like when I first went abroad in Netherlands, I could see that the machines were cleaning the roads. And now in Delhi, in Delhi airport, you can see that machines are cleaning the roads. So that's where those things. In fact, nowadays you can buy cleaning devices which can automatically operate and go to every corner of the room, and it can clean easily. And Alexa is one of the examples of AI, and these things are very very important in current scenario. So, what is the distinctiveness of Industry 4.0? Proponents of the fourth industrial revolution suggest it is a distinct revolution rather than simply a prolongation of third industrial revolution. This is due to the following characteristics. First is velocity, that is exponential speed at which incumbent uh, industries are affected and displaced, and the scope and systems impact. So large amount of sectors and firms that are affected, and paradigm shift in technology policy. New policies designed for this new way of doing are present. An example is Singapore's formal recognition of Industry 4.0 in its innovation policies. And in fact, Germany was the first country which introduced the technological policy on Industry 4.0. And critics of the concept dismiss Industry 4.0 as a marketing strategy. They suggest that although revolutionary changes are identifiable in distinct sectors, there is no systematic change so far. In addition, the pace of recognition of Industry 4.0 and policy transition varies across countries, and the definition of Industry 4.0 is not harmonized. One of the most known figures is Jeremy Rifkin, who agrees that digitalization is the hallmark and defining technology in what has become known as third industrial revolution. However, he argues that the evolution of digitalization has barely begun to run its course, and that its new configuration in the form of Internet of Things represents the next stage of its development. Now, what are the components that govern Industry 4.0? So, the application of Industry 4.0 operates through mobile devices, Internet of Things, location detection technologies like electronic identification, and advanced human machine interfaces, and authentication and fraud detection, smart sensors, big analytics, and advanced processes, and multi-level customer interaction and customer profiling, augmented reality, variables, on-demand availability of computer system resources, data visualization, and triggered live training. Mainly, these technologies can be summarized into four components, defining the term Industry 4.0 or smart factory, like cyber physical systems, Internet of Things, on-demand availability of computer system resources, for example, cloud computing and cognitive computing. So, Industry 4.0 networks a wide range of new technologies to create value, and using cyber physical systems that monitor physical processes. A virtual copy of the physical world can be designed. Characteristics of cyber physical systems include the ability to make decentralized decisions independently, reaching a high degree of autonomy. The value created in Industry 4.0 can be relied upon electronic identification, in which smart manufacturing requires said technologies to be incorporated in manufacturing process to thus be qualified as in development path of Industry 4.0 and no longer digitization. So we have to be careful also in cloud computing, because like many of you would have seen that now Google is uh, sort of encaching this Google Drive data space, and most of you have 15 GB data, and now you have to delete files. So like it's like sort of ransom that that either you keep it or delete it, or you pay like 1,500 to 2,000 rupees for keeping data from more than 15 GB to 100 GB. So this is one example where they are encaching their Google Drive. So initially they provided it for free. So nowadays people are not keeping their hard drives, and they are buying space on Google Drive and actually uh, placing their data. Especially when we work with machines, for example, I was working on a beer machine, and there is data of profilometer, and it cannot come in pen drive or in Google, and we need 1 terabyte of data for small experiments. Then that data can be only put on cloud. So these technologies are very very important, and we have to keep an update on that. Now, what are the primary drivers for Industry 4.0? That is digitization and integration of vertical and horizontal value chains. And Industry 4.0 integrates processes vertically across the entire organization, including processes in product development, manufacturing, structuring, and service. Horizontally in Industry 4.0 includes internal operations from suppliers to customers, as well as all key value chain partners. The second is digitization of product and services, like integrating new methods of data collection and analysis, such as through the expansion of existing products or creation of new digitized products helps companies to generate data on product use to define products. And the third one is digital business models and customer access. So, customer satisfaction is a perpetual multi-stage process that requires modification in real time to adapt to the changing needs of the consumers. Now, what is the role of 3D printing in Industry 4.0? So, the fourth industrial revolution is said to have extensive dependency on 3D printing technology. And some advantages of 3D printing for industry are that 3D printing can print many geometric structures as well as simplify the product design process. It is also relatively environmentally friendly. In low volume production, it can also decrease lead times and total production cost. Moreover, it can increase flexibility, reduce warehousing costs, and help company towards adoption of a mass customization business strategy. In addition, 3D printing can be very very useful for printing spare parts and installing it locally. Therefore, reducing supply dependence and reducing the supply lead time. So it's a very very important technology, and we can print on demand also, because it is for like a small component. Generally, at the moment we are not operating for large components, but this is like a future that because in subtractive manufacturing, so that is the opposite of additive manufacturing. In additive manufacturing, we are adding the material layer by layer, and in subtractive manufacturing we have a casted item, and we do it machining, polishing, and so many things after production. Polishing is there. So that lead to removal of material and a lot of loss of material. But at the moment that was like cheap technology, and now we are entering into 3D printing technology. Though it is expensive, that but it is very very useful in medical industry, because like let's say we want to make a small medical implant. So in medical industry, the cost does not matter, because it's like about life and death. So it's very very important technology in medical industry, because the cost does not matter there. It's a question of life, so it's very very important. And in defense applications also, it is greatly used. But for like where we need very very low cost, only the traditional printing or traditional manufacturing is applicable. The determining factor is the pace of change and the correlation of the speed of technological development, and as a result, socio-economic and infrastructural transformations within human life allows one to state a qualitative leap in the speed of development, which marks a transition to a new era. Now, as I said before, also we can see that this is the skull that has been produced completely by additive manufacturing. Now look at the complexity of the part, and it cannot be made using traditional manufacturing. This can only be made using additive manufacturing, and this is like very very important in medical industry. So additive manufacturing has emerged as a promising technique to manufacture complex structures using metallic, ceramic, and polymeric materials directly with the better mechanical and microstructural properties. In fact, we can tailor the mechanical and microstructural properties. And as I said, we can make functionally graded materials also, where the composition of material is changing from one side to another side. In fact, like naturally made functionally graded material, one example is bone itself, because bone has a different density on different sides. So inside it has a different density, and outside it has a different density. So such material can only be produced using additive manufacturing as compared to conventional routes such as casting and powder metallurgical techniques. Now, you can see these are the typical examples of additively manufactured components in various industries. You can say the cycle is like a single component. So you can produce it in just one go. We don't have to like assemble the parts individually. Now, coming on to like the basic definition of additive manufacturing, or we can call it a 3D printing, is a process of joining materials to make an object from 3D model data in a layer by layer process, and it is a suitable process to complex metal net shape part and not just prototypes as earlier. So manufacturing actually can be divided into two branches: additive manufacturing and subtractive manufacturing. So in additive manufacturing, we print it layer by layer, and any component, like first we make a 3D model data and stereolithographic file, SLS file, and then we do like slicing, and then it can create a G code or M code, and then it can print using machine. So we will give the print command, and then it will print a 3D print. And in subtractive manufacturing, we will have a big like cast part, and then we will machine it, and grinding, polishing, so many things happen, milling, so many things happen for, and there is removal of the material. So there is significant loss of material in this, but this is still a cheaper option. And this additive we use for only high-end applications at the moment, but we are the technology is now able to reduce the cost also. So this is because of the technological advancement, and the cost has reduced significantly, especially when the industry is putting a lot of money. So the cost is definitely going to be reduced. Now, there are various names for additive manufacturing which you will see in literature and in various papers. For example, one name is 3D printing, and second, rapid prototyping. So the initial name was only rapid prototyping because generally when it was used in earlier days, it was only to make a prototype. So the technique was named as rapid prototyping. Then the name came rapid manufacturing, then additive layer manufacturing, then laser beam melting. So when the power source for melting is laser beam, then it is called laser beam melting. And selective laser melting (SLM) process. So this is generally in powder bed fusion. So this is called selective laser melting, and then selective laser sintering. So in selective laser melting, actually we are going above the melting point. In selective laser sintering, we are below the melting point. And in then direct matter laser sintering and electron beam melting, free-form fabrication, solid free-form fabrication, laser metal deposition, laser cladding. So laser cladding we say when we only deposit just one layer or two layers, then we say laser cladding. But we have multiple layers, then we say additive manufacturing. Then direct energy deposition. So in direct energy deposition, actually the energy that is, for example, laser and the metal powder is they are deposited at the same time. So that's why it is called direct energy deposition. And then direct metal deposition, one and the same name. And then also like wire arc additive manufacturing, where we are adding the material using wires instead of powder. And then powder wet fusion. So powder wet fusion is the same as SLM. So why use additive manufacturing? So additive manufacturing is used to produce custom-made implants according to the data for patient acquired via computed tomography and to reduce waste and increase the design freedom compared to conventional casting and machining. The possibility to create a porous complex structure to improve OCO integration and mechanical properties, so that best match with the modulus of elasticity of local bone, thereby reducing stress yielding. And they provide control on the geometry of cells and strut and relative density within the implants as needed. The fast cooling rate, which provides homogeneous microstructure. So in this technology, actually the cooling rate is of the order of 10 raised to 6 degrees centigrade per second. So what do we mean by 10 raised to 6 degrees centigrade per second? Does it mean in 1 second the temperature is decreasing by 10 raised to 6 degrees centigrade? No. The actually we have to rewrite it as like 10 raised to 3 degrees centigrade per 1 millisecond. So that means in 1 millisecond the temperature is decreasing by 1000 degrees centigrade. So this is a very high cooling rate, and it provides homogeneous microstructure. In conventional casting, generally the cooling rate is 100 degrees centigrade per second. So the microstructure of the implants can also be customized based on each patient's needs and conditions. 3D printed metal implants could last longer than regular implants and be more durable and potentially save the medical industry money it so desperately needs. And also, so this is the like typical knee implant. This is the titanium implant. Actually, at the moment, the technology readiness level of titanium implants is like 9 for additive manufacturing. I'm talking about additive manufacturing. So that is like very very good. And for we want to replace these implants with magnesium implants because like uh, rate of dissolution of magnesium is very very fast. So we want to control the rate of dissolution of magnesium in blood, and we want to make it equal to the bone growth. So if the bone growth the rate of bone growth is equal to rate of dissolution of magnesium implant, then actually what will happen? We will implant the magnesium implant inside the human body, and as the time grows, the implant will dissolve in the body, and the body will regrow the bone. So actually, we not need not to do resurgery, which is the case in case of titanium implants. For example, in titanium implants, we need to replace the implant because the bone will grow. So we will need to do resurgery, and if we need to do resurgery, you can imagine how painful it is going to be for patients. So additive manufacturing can play a very very important role in reducing that pain of the patient. So it's very very important, and it will not matter how much expensive it is if it can reduce the pain of the patient. Now this is the typical hip implant. So this is the additively manufactured titanium alloy structure used in biomedical implant. And this is the sternum and rib cage. If someone has car accident and his ribs are broken, and this is how it looks like. So these are the real titanium implants. In fact, where I worked in Obscene Medical Private Limited, they have very good medical implant facility, and they are one of the best manufacturers of additively manufactured magnesium implant. At the moment, titanium implants are very very successful, not any other metal. This is the acetabular cup, and this is the prosthodontic implant, like teeth are there. Now, what are the uses of additive manufacturing? The use of additive manufacturing technology is developing in many industries like aerospace, energy, medical, in particular surgical implants and dental applications, then tooling in particular for plastics processing, automotive and transportation, and consumer goods, etc. Now, this is like a type of additive manufacturing. So, metal additive manufacturing can be divided into two types. First is powder bed technology, and the second is blown powder technology, that is direct energy deposition or laser metal deposition. And powder bed technology can be further divided into laser beam melting or electron beam welding or 3D printing or inkjet printing. So green parts bound by winder and final solidification by sintering. Now AM process can also be uh, classified based on whether it is liquid or powder or solid. So, liquid waste process can be classified into stereolithography, jetting system, direct light processing, and selective laser. Then powder-based process can be classified into selective laser sintering, three-dimensional printing, fused metal deposition systems, electron beam melting, selective laser melting, selective masking sintering, selective inhibition sintering, electrophotographic layered manufacturing, high-speed sintering, and in solid-based additive manufacturing process can be divided into fused deposition modeling, seed stacking, and technologies. So, should we take a break for 10 minutes, Professor Jitendra?
Yes, sir. Yes, sir.
Hello?
We will take a break of 10 to 15 minutes.
Yes.
And Gaurav Sahu sir is requested to post the feedback form. And dear participants, please take a rest of 10 minutes, and after that we will again meet here in this, and you will
Okay,
get
sir.
a
Thank you, sir,
feedback link in
for the
the
session. Now I
chat
request
box.
participants to fill the feedback form as you received, and we will again join back for session 2 after 10 minutes. Thank you.
Okay, thank you.
गौरव सर फीडबैक फॉर्म एक बार फिर चैट बॉक्स में डाल दीजिएगा, वो बार बार नेटवर्क का कुछ होता है तो फिर दिखता नहीं है feedback form.
Yes, that
Feedback
will
form,
do.
Aditya sir, if you are having the link of feedback form, then please forward it.
आदित्य सर फीडबैक फॉर्म चैट बॉक्स में डाल दीजिए. आदित्य सर लेट कर दिया सर.
Yes, sir. Wait for a minute, sir, please. I'm calling.
Yes.
डॉक्टर साहब फीडबैक लिंक डाल दो. जी. Feedback link is being posted in the chat box. Participants is requested to give the feedback. सर नमस्कार. सर नमस्कार.
ओके सर. ओके सर.
हाँ, वो अब शायद वो बंद कर देंगे.
अभी चालू है ना, अभी बात हो गई मेरी. मैंने कहा भैया बंद करो, वो बच्चे आपको बोलने खरे अंकल का फोन आ रहा तो सुनना ही पड़ रहा है.
अरे वो अभिषेक तिवारी की.
नहीं आपने वहाँ वही शुक्ला.
अच्छा, वो भी थे क्या मीटिंग में?
है ना.
अच्छा, उनके बिटिया का आवाज आ रहा था. नहीं, अरे मुझे लगा कि अभिषेक तिवारी को उसमें आ रहा है. अरे
वो उनका है.
अच्छा. मुझे लगा कि वो
जब से लगा रहे तो ना बोलने की नहीं, तुमने उठाया नहीं. वो बिटिया भी आई बोलने की पापा खरे अंकल का फोन अभी कर रख दो, अभी जीता है.
अच्छा, मैं उनका सोच रहा था. अभिषेक तिवारी जो अपने स्पीकर है ना,
जिसकी आवाज आती है ना तो उसका ब्लिंक होने लगता है.
हाँ.
उनका ब्लिंक लगता था जैसे वो
हाँ हाँ,
बोलते
मैं वो नहीं देखा मैं। बढ़िया, आज महामहिम ज्वाइन कर लिए, बड़ी बात है।
सवेरे टोका भी था ना।
अच्छा, डायरेक्टर सर ने भी टोका है उनको?
हाँ
हम वो पूछ रहे थे तो हमने बता दिया उनको जो था। अब क्या
हाँ।
झूठ थोड़े बोलेंगे कि ज्वाइन कर रहे हैं।